So in the last seminar, I roughly introduced the bicategory LG. And I'll just give you a brief reminder of that. So the bicategory LG has objects which are isolated hypersurface singularities. And one morphisms. Well, the way you'll find it defined in the literature is as matrix factorisations, but the way I presented it last time was to say that a one morphism from an isolated hypersurface singularity with equation F to an isolated hypersurface singularity with equation G that those are Zariski closed, that is defined by polynomial equations, Zariski closed subsets of the form X of the vanishing locus of G minus F. And that's contained in Cn cross Cm, where there are n x variables and m y variables. So that's the set of all a1 through an's, b1 through bm's, such that g of b is equal to f of a. All right, I gave some examples last time, and the focus of this seminar is the question of how to compose such one morphisms. So to define a category is to define objects, morphisms, and a rule for composing them. That's the actual operation in that algebraic structure, much as the group multiplication is the operation in a group. So clearly it's important, this structure. And in a bicategory, it's the same. So you have objects, one morphisms, and two morphisms, and a rule for composing one morphisms, and a rule for composing two morphisms. We'll say more about the two morphism story later, and for now I want to focus on sketching at least. I won't even define how to compose one morphism, but I'll try and give you some flavor for what is interesting about that, and especially I'll focus on a computational point of view. So today, what is the geometric and perhaps also computational content of this composition? So I'm going to leave the hard work of actually defining composition in general to Rohan, and I'll just steal the fun job of talking about the geometric content in a sort of special case. Hopefully that helps to motivate the suffering that Rohan will deliver to you. Maybe he can deliver it in a way that involves no suffering at all. We'll see. Okay. So I'm going to briefly remind you of the example. Which involved permutations. So given an n, we define for sigma in Sn the following points of view on the same object. So I think I called this like algebraic ideal last time, and then there was sort of geometric, and then there was algebraic, but from the point of view of modules. So the ideal, which cuts out the graph of this permutation, viewing it as acting on tuples of complex numbers, is given by the equation that says that the first coordinate of the output is the sigma first component of the input. That's how you map a tuple of n complex numbers to its permutation. So that's an ideal in the polynomial ring in 2n variables. The actual graph itself, which is the set of 2n complex numbers that make all of those equations 0. That is v of I sigma. That's, remember, means the vanishing locus. Just a second. For the purposes of the recording, I have to make sure that the screen on my laptop is not going off all the time. Hopefully that will not happen again. And that's the graph. So that's the set of all tuples, where that's a tuple of n complex numbers, a underline, and then I have f sigma applied to that, where f sigma is yet another piece of notation. That's the actual function which performs the permutation. Then I've got the module, which is just the coordinate ring of gamma sigma. It's the quotient of the polynomial ring by I sigma, viewed as a module over the quotient by W, where W has not played any role up till now, but it was selected to be this thing here. And the role of this in the story I'm about to tell is meant to seem a bit mysterious. So what I'm going to talk about today is just how to compute with these ideals and sort of compose. So I want to talk about how to think about composing functions like this from the point of view of ideals, from the point of view of geometry. So this is ideals, this is the geometry, and these are the modules down here. It's only this latter category, algebraic / modules, that actually involves M sigma, and therefore W. The first two don't involve W at all, and W won't really play a role today. So maybe I'll just briefly comment that in order for the story to remain finite in some categorical sense that we'll return to later, you sort of don't want to talk about these ideals on their own. You need to view them as contained in, ideals over some principal ideal generated by a W, which is an isolated singularity. That's a kind of way of making things finite, but that's not meant to make much sense right now. So the role of W will come back, and I don't want to focus too much on it today. Okay, so as I just said, there are 4 different points of view on composing these permutations that I want to talk about. The first is, so let's just call this composition, and its composition as, well, functions. So f tau and f sigma as functions. In some sense that's obvious. Well, you can also just compose directly from the graph and graphs. And if you're kind of switched on, you might be sort of confused as to why I'm distinguishing those two things, right? Because set theoretically, actually, f tau and f sigma are their graphs. There's no difference set theoretically between a function and its graph. But we think about them differently, so that's why I'm giving them different tiles here. We could also try and view the composition from the point of view of the ideals, that is, the equations that cut out those graphs. And finally, we can try and view the composition from the point of view of the modules, which are the relevant rings of functions on those graphs. And probably we'll only get through 1, 2, and 3 today, and 4 is in any case more subtle, and this will eventually lead us off in the direction of derived tensor products and matrix factorizations. But that's probably for the future. What I want to do and really try and be clear about is the role of geometry in talking about 1, 2, and 3. So I'll talk about elimination ideals and some basic algebraic geometry there. Okay. So maybe there's a conceptual point that I'll emphasize already, which is you can compose these functions without any of this business, right? I mean, I could write down these permutations and just compose these functions, and that's in some sense the end of the story. However, if you view the function as a graph and the graph as a geometric object, then it lives in a geometric world, and there are other geometric objects that know about it. For example, the ring of functions on it, or there's a sort of universe of geometric objects that relate to that graph. And then you can ask, well, how do those objects behave when you compose? And if you dig into that, you start to see interesting structure, which arguably is sort of lying behind what you thought was a straightforward operation when you compose those functions. And that's going off in the direction of computation, but it also illustrates part of the rich and interesting structure of this bicategory. So I'm sort of choosing that as a way into the topic. Okay, so that's enough preamble. Let's get into some details. Okay, so 1, composition of functions. Well, there's actually one wrinkle here. So if you compose f tau with f sigma, I mean, that's got to be f. Is that f tau sigma or is that f sigma tau? Well, let's do a calculation. Have a guess if you beat me to it. So f tau f sigma of A is f tau of that. Now what does f tau do? Well, it takes the entry in position tau 1 and sticks it in the first position of the tuple. Right? And if you think about what's in position tau 1 of that sequence, well, it's A sigma tau 1. You might have been tempted to write down tau sigma 1 because it kind of looks like that's what you did when you'd applied this, right? You just sort of stuck a sigma in front of the index. But if you think about it, I think you'll agree that this is the correct calculation. And that is f sigma tau of A. All right. So that looked right, but it's actually wrong. Okay, so f tau f sigma. I mean, I could have defined the action of f sigma differently so that it lined up, but somehow from the ideal theoretic point of view, this is kind of natural. So this equality here is going to be something I'll talk about quite a lot. So let me call it star. The equality star, it appears to have no content. Right? You could say, well, there's a calculation here, and maybe you could argue it has, 2 steps, and that somehow those 2 steps might be the content of that equality. If you have a logical background, you'll be familiar with Frege's distinction between sense and denotation. So you might say that that calculation is the sense of that equality, but that's all kind of metamathematical / philosophical. It doesn't really appear in any concrete way at a mathematical level. So that's all I have to say about 1. You compose the functions, that's it. There's something more to say about this story at the level of the graphs, though. Which, as I said, is not really any different from composing the functions, but we do think about it differently. So let's try and write down the composition cognizant of the fact that the function really is just a set of tuples. Right, so how am I going to write this? So remember that gamma is the graph of f. And if I was to compose the function f tau and f sigma, but using their graphs, and I'll just write it like this. So this thing here means the graph of f tau composed f sigma. So what I'm writing down here is just the definition of the composition of two functions in set theory. So the composition is a set of pairs where, so this is the input to the first function, and this is the output from the second function. Well, that's all those tuples AC, which are sort of the concatenation of an input and an output, and another input and an output. That is, they're the pairs AC for which there exists an intermediate B with AB in the graph of the first function and BC in the graph of the second. So here's a fancy pants way of thinking about that. Well, maybe I'll first remark that this exists is important. So exists is sort of related to direct image. Well, let's just say image for the present moment. If you're used to thinking about the realization of quantifiers in topos theory, this connection between image and pullback, and the quantifiers will be kind of visceral to you. Otherwise, maybe this doesn't make much sense, but it will in a moment. So I want to recast this equality here, or rather this combination of an existential quantifier and there's actually an and here, right? Okay, so there's that existential quantifier. I want to recast it as an image in the sense of there's a function and you take the image of some set under it. And this I want to recast as an intersection. Of course, conjunction and intersection are closely related. And these are geometric ideas, taking the image and taking the intersection. Those are geometric things. So that'll start to move us towards a geometric picture. Okay, so here's the diagram I want you to consider to think about this way of composing f tau with f sigma. I want you to think about the graph of f sigma sitting inside Cn cross Cn. I want you to think about the graph of tau also sitting inside Cn cross Cn. And then sitting over both of them, I'm going to put the triple product. This function here, I'm going to call it pi12, is the projection onto the first and second factor. So pi12 of ABC is AB. And pi23 of ABC is BC. And then I've got a third projection, which is the outer 2. So pi13 ABC is AC. All right, so now let me use this diagram and these three maps to rewrite this definition of the composite. So let me take the image under the outer projection of the pre-image under pi1, 2 of the graph of sigma, intersected with the graph, the pre-image of the graph of tau. Now, I kind of prepared you to think about this as being related to the previous formula, because the image is kind of like exists, and this is like and here you see gamma sigma, and here you see gamma tau. So let's do the calculation and see that in fact that set there, which remember pi1, 3 maps to Cn cross Cn, I claim that set is the graph of the composite, the thing I was calling gamma tau circle gamma sigma before. So what is this? Well, if I take the image, that's the set of all things in Cn cross Cn, for which there exists a tuple in the domain, which remember is a triple product of Cn with itself. Let's say for which there exists A prime, B prime, C prime, with pi1, 3 of A prime, B prime, C prime equals AC. And A prime, B prime, C prime actually in that thing inside these two brackets. So that's pi1, 2, gamma sigma, pi2, 3, gamma tau, bracket. Well, to say pi1, 3 of ABC of A prime, B prime, C prime is equal to AC is simply to say that A prime equals A and C prime equals C. Right? So I can just make that substitution elsewhere in the formula, and so that exists becomes actually an existential quantifier over only the B prime. Right? So there exists B prime such that A, B prime, C is in that intersection. Well, I'll just do them separately. That's A, B prime, C is in pi2, 3 inverse gamma tau. Now let's think about this first inclusion. Pi1, 2, well, pi1, 2 is the projection, right? So if I take the pre-image under a projection, the third component is just free. Right? Because it's just discarded by the projection. So that simply says take the pre-image under pi1, 2 of gamma sigma is all those tuples where the third component is free and the first two lie in gamma sigma. So that's simply all those ACs for which there exists. I'll just switch to writing B instead of B prime, with AB in gamma sigma, and similarly for the second condition. So that's and BC in gamma tau, which was of course the composition as claimed. All right, what was the point of all that? Well, we recast the composition of graphs, which is just the composition of those functions, in terms of, I'm up there in scare quotes because, you know, at this point they're just kind of set theoretic operations, but in terms of geometric operations, taking the image under pi1, 3 to be precise, and the intersection. Any questions at this point?
None from me.
So I've talked about 1 and 2 now. Let's move on to 3. So how can we recast all of this in terms of ideals? Well, if we look at this formula at the top of the page here, pi 3 image of intersection. Well, we can turn this into an ideal and this into an ideal. And if you're going to take the intersection of the vanishing loci of two ideals, that just means adding the ideals. So you could imagine this sort of becomes a plus of two ideals. The real question mark is at the level of ideals, what does taking the image mean? And that's actually what's interesting. Both here and in the story about composing one morphisms in LG, and also in its kind of computational content. All right, so three. Composition of ideals. Let's just say as ideals. I don't want to suggest there's like a general way of composing ideals. Maybe let me just reload this image into your head. So this diagram was the basis of the story I just told, right? So you've got these three projections, pi 1, 2, pi 1, 3, pi 2, 3, and you've got the triple product sitting up on top of everything. So now think about replacing this by a polynomial ring in x, y, z, this by a polynomial ring in x, y, this by a polynomial ring in x, z, and this by a polynomial ring in y, z. And those projections correspond to the inclusions of those polynomial rings. So that's the diagram I'm now going to draw. So we have C, X, Y, Z, sitting inside which is X, Y. I won't give a name to this because I think I don't need it. And those inclusions, over here in the other diagram it was gamma sigma, that corresponds to the coordinate ring modulo I sigma, and this is I tau. Oops. Okay, so as I said, the intersection pi 1, 2 intersect pi 2, 3 corresponds to an ideal. I'm going to call it I. To really explain why this is the correct ideal, I'd have to teach you a little bit more algebraic geometry. Those of you who sort of know how to correspond ideals and closed sets will probably follow this. I'm just going to sketch the reason. So taking the pre-image corresponds to taking the ideal I sigma, which lives in here, and extending it along this map. That is, I view I sigma as a subset of this polynomial ring, which is in some sense tautological because it involves polynomials in x, y, and x, y live here as well. So just take all the polynomials in I sigma and read them as polynomials here, and take the ideal generated by them, but in that bigger ring. That's what this means. And do the same with I tau, and then add them together, taking the intersection of closed sets as corresponds to adding ideals. All right, so that expression for I corresponds precisely to that formula with the pre-images and the intersection. Now, we know what I sigma and I tau are, right? So let me just write out the generators. So the generators I get from I sigma here involve the y variables and the x variables, and they look like this. Okay, so the part of the story I'm missing is the bit that corresponds to taking pi3 image. So at the level of ideals, what does that mean? Well, it's actually a little complicated. Taking images is the most complicated thing you can do at this level, but basically anywhere. So taking derived direct images of sheaves is taking sheaf cohomology. That's the most complex part of, well, one of the more complicated parts of geometry. So taking pullbacks is simple. Taking images is where all the content of geometry is in some sense. So it isn't easy to give us, there's no straightforward answer to what it means to take the image under pi13. In this case, however, it is straightforward, and I'll explain how to understand that, but in a general context, using elimination theory. So, well, what does taking the image mean? In the case where we're composing graphs, we saw that it meant taking, this mapping and kind of plugging it into this one, right? Which, if you like, is deriving the consequences for the relationship between the x's and z's that come from the intermediate relations with the variable y. So taking images, it should give us y something minus, should be no y's left, z something minus x something. Those are the relations we're looking for when we want to take the image, right? Because taking the image means giving some subset of this polynomial ring. There's no y's allowed here anymore. So we're looking for the consequences of these relations for x and z. And of course we can work out what those are. Maybe I'll do that. Well, I'll shove that down in the corner here, or try to. So we have zi minus y tau I, and we also have the relation which is y tau I minus x sigma tau I. So if we add those together, we get the relation which is zi minus x sigma tau I. And of course we recognize that as the defining equations of the graph of the composite of the two functions. All right, but what is the generic method for going from an ideal like this that involves this intermediate variable y and getting it to spit this out? All right, so that's the final topic I want to talk about today. So it might seem like this is a very particular example with these permutations, and of course it is, but it's chosen to illustrate a broad and, I would argue, quite deep point. Okay, so here's a very brief introduction to elimination theory. We may come back to this or not, I'm not sure. I'm going to just assume you know what Grosvenor bases are and proceed. Probably you don't, but that's okay. The point is to illustrate an idea, not to really have all the details be clear. So I'm trying to communicate how you eliminate variables. The technique for doing that is what are called Grosvenor bases and the Buchberger algorithm. Okay, so to use Grosvenor bases, you have to choose an ordering on your variables. So I'm going to choose all the y variables to be greater in the ordering than the x variables, and they're greater than the z variables. So I'm going to use the lexicographic monomial order on Cxyz. Okay, so we start with the equations that involve the y's. That is, we start with this set. to eliminate the y variable, the trick is to find what's called a Grosvenor basis of the ideal generated by the set G, which is of course the ideal I that I've been talking about. So how do you find a Grosvenor basis of an ideal? Well, you run something called the Buchberger algorithm. I'll post notes that have the full calculation in it. I'll just sort of skip to the conclusion. So what the Buchberger algorithm does is it looks in your equations, derives certain consequences of them, and in a sense produces a set of consequences of your original equation which have a certain good property with respect to Euclidean division. Maybe that's the best I can do in one sentence. But the output is recognizable, so what it does is it starts with our original equations and it gives us those consequences that I just mentioned. So it ends up giving us the original set, but also these relations between z and x. So the main theorem of elimination theory tells us the following, and this essentially implements taking the direct image on the pi13. It says that let me call this G infinity, just because it's the end result of this algorithm. So the elimination theorem says that if I intersect that final Grosvenor basis with the smaller polynomial ring, so this is the thing in my diagram on the previous page, the vertex that sort of was to do with the place where pi13 ends, right? If I perform that intersection, that is a Grosvenor basis, in particular a generating set, of intersecting that ideal with CXZ. Without Grosvenor basis, it's not clear how to find a generating set for that intersection, right? But we know what that intersection here is, right? Look at the original set. Everything in there involves the y variables, right? So G intersect CXZ is the empty set. So the only part of G infinity that intersects the polynomial ring in x and z is the new stuff. So this here is just those new equations. All right, so the elimination theorem tells us that those new equations that involve only x and z do in fact generate the intersection here. And there's a further step, which, I mean, the actual statement is more, in full generality, is more complicated than the story I'm sort of presenting here, so I don't want to give the full theorem, but what it says in this case is that this actually cuts out the image. It says that the vanishing locus of that intersection actually is exactly the image under pi13 of the vanishing locus of I. All right. Well, you'll recognize, I mean, this was, remember, pi12 inverse intersect pi23 inverse, and there's the pi13. So this stuff on the right-hand side is the graph, or the composition of the graphs or the graph of the composition. And what I've shown you is a way of, sorry, the aircon's just come on here, hopefully it's not too loud. I've shown you a way of thinking about that graph in terms of the vanishing locus of some sort of polynomial equations. Just a moment, I'll try and turn this off. Okay. All right, so that is the geometric way of thinking about composing those two graphs. It's to arrive at this set of equations, the intersection of I with that polynomial ring, and behind that was the process of finding the Buchberger algorithm, which found that basis and did it by deriving these consequences of the original equations. Okay. Maybe I'll just conclude. So hopefully that seems kind of curious, but what's that got to do with LG? So what does this say about composing one morphisms? In LG. Well, here's where W comes back. All right, so I said W would not play much of a role here, but remember W was the difference of a sum of squares. So the way I defined this was that the objects in LG were isolated singularities. There's 3 of them. And the morphisms were Zariski closed subsets of the vanishing locus of their difference. Now, as we discussed last time, this is in fact a subset of that vanishing locus. Okay. So how do you compose those two things? Well, there's a general rule involving tensoring matrix factorisations, which is a kind of derived tensor product. But what I've prepared you to think about today is just in general how you might think about composing the functions whose graphs are gamma sigma and gamma tau. And what we saw was that the geometry behind the role of W here is obscure, right? And it's obscure because it's not simple. But if you ignore W and just try and compose the functions whose graphs are gamma sigma and gamma tau, then the geometry behind that involves well, I'll just write out the formula one more time. It's an image of an intersection and the way we thought about was that was in terms of a Grosvenor basis of taking the defining equations of those two ideals, so that was the yi's and the zi's, adding them, computing a Grosvenor basis, and then intersecting this with the outside variables. Now, there's a general rule for composing in LG, which we'll discuss, and at least in the case of quadratic forms, you can recognize in that sort of general rule these ideas as a sort of general method. So this is a kind of geometric deduction, right, of taking two sets of facts, y is equal to x and z is equal to y, and deriving a fact, which is that z is equal to x, and that the derivation in this case takes the form of computing a Grosvenor basis. Okay, so I wanted to hint at some of the geometry that lies behind composition. I've done that in the case of these permutations, or at least pointed you in the direction of elimination theory. I'll come back to this exact example once composition of one morphisms has been formally introduced. So this is the end of the heuristic part, really. So what we're going to now do, or rather Rohan will do part of it, we'll do part of it, and I will do part of it, is to explain how to replace these things by matrix factorizations, which are kind of homological algebra avatars of these Zariski closed sets, and then how to take, so maybe that's y, tau, this is replaced by something that you might call y sigma, and then the composition is associated to something that looks like a derived tensor product of those two things. And that derived tensor product, it knows about sort of the first, second, third, fourth, and so on order consequences of these equations. And that's what's sort of packaged by the derived tensor. So that's a brief sketch of the geometry involved in defining and understanding and computing these compositions. So I think I'll stop there. Any questions?
Yeah, I suppose I was wondering what goes wrong with setting up LG like this. Like, where do you sort of run into a difficulty with actually proving this thing's a bicategory? I suppose two morphisms.
Well, that's one problem. Yeah, I mean, there's no obvious way to define two morphisms when you set it up this way. If you set it up this way, there's no obvious role for W, right? It just takes Zariski closed sets and you do your thing. You can do that. That's a category of correspondences, and it's something in algebraic geometry we do consider, but it's not in any obvious sense a bicategory, so that's one thing. The second thing is that, well, I mean, you could just take the derived category of, well, to introduce two morphisms would be to replace these Zariski closed sets by some kind of modules, and the obvious choices there are the coordinate rings of those closed sets. So you could just say two morphisms are just maps of modules between those coordinate rings. That wouldn't be interesting. You could say you could take morphisms in the derived category. That would be more interesting, but then in some sense it would be highly infinite and not really capture much about, well, it would just be hard to think about. It wouldn't really be an interesting structure, I think. So, however, once you kind of throw away a lot of that information, you mod out by perfect complexes, you do get the story with matrix factorizations. But you're introducing W at some point there.
Yep, sure.
Yeah. But I think the real answer is that, okay, supposing you introduce W, you could still set it up in this way and talk about Zariski closed sets instead of matrix factorizations. But then you see, when you actually compose these things, you'll escape that universe. I mean, the composition of two things that look like this, and if you, in LG as we're going to define it, if you compose two matrix factorizations, one corresponding to gamma sigma and one corresponding to gamma tau, you would get a matrix factorization corresponding to the function f tau after f sigma. But in general, if you do that, so you take two matrix factorizations, each corresponding to a Zariski closed set, and you compose them, you won't get a matrix factorization that corresponds in any obvious way to something you could construct from those closed sets. So that's, I suppose, the real answer. For an example, I mean, a good example of that is Kovenov-Rosansky homology. So I could give you pointers to a kind of concrete example where you get something very strange out when you compose two relatively innocent-looking objects.
Yeah, sure. Thanks.
Other questions?
No more from me.
Cool. Okay, maybe we'll leave it there. There's a cryptography session after this, but otherwise I'll catch you guys later.